to Unit 10, Notes A. We're going to focus on reaction rates today. So when you look at the rate of a reaction, what you're really looking at is how quickly the reactants are turning into the product. This isn't an instantaneous thing. It takes time. And how much time is something that will determine as the rate. So this is kind of a picture representation of red being all reactants, and then the blue would be the products. So as the reactants are used up, we see less and less of them, and then as we're making products, we see more and more of those. We can actually graph this, showing a decreasing concentration of the reactants and an increasing concentration of the products. Some reactions occur really quickly, like a rocket ship launching. Some reactions occur really slowly, like watching paint dry. And then, of course, there's reactions that are everywhere in between. So how do we calculate reaction rate? Well, in order to find the average rate of a chemical reaction, we're going to look at the overall change in quantity, some type of amount, maybe a molarity, and we're going to look at how much time that takes. So we're looking at the change in time. Notice the lowercase t for time. Capital T would be our temperature, so we're looking at change in quantity over time. So let's look at an example here. A lot of reaction rate questions are going to come out of tables, they're experimental questions. So we can see the table down here that at the 0 time, meaning at the beginning of the experiment, I had a concentration of reactant of 0.22 molar. Then as I let 4 seconds pass, the concentration goes down to 0.1 molar. So I'm going to look at the change in concentration, or my change in quantity, as it compares to that 4 seconds. There is a very specific formula though, right? We had change in quantity over change in time. Whenever you have that delta symbol, it always means final minus initial. So we want to look at the final concentration, subtract the initial concentration, and be careful to do the same with the times. This is going to have some interesting things come up as we start looking at the signs created from this. So let's start plugging this in. Let's find our average rate. So the concentration final would be the one at the end of the experiment, at the end of 4 seconds. So it's going to be the 0.100. We can tell from the brackets that we're going to be plugging in concentration in molality. So we've got that here. Now we're going to subtract the initial. So what was it at the beginning? That was the 0.220. So minus 0.220 molality. And then on the bottom, I'm going to do again final minus initial. So I end at 4 seconds, 4.00 seconds. And I started at 0 seconds, the initial time. Notice it is 0.00. These would be significant zeros based on the tool used to measure time of the timer. So 0.00 seconds. So when you subtract the when you subtract the 0.22 from the 0.1, when you do the top subtraction, you're going to get a negative top number because the larger number is after the subtraction sign. Whereas when you do that to the bottom, 4 minus 0 is a positive 4. So you are going to end up with a negative answer since only one component is negative. And that top subtraction turns out to be a negative 0.120. So your final answer is negative at negative 0.0300 molarity per second or moles per liter per second. So what does that really mean? Well, it depends on where the negative came from. If the negative is in the top part, if it's coming from the quantity part of the formula, then that would indicate a decreasing concentration. If a negative sign were in the bottom part, that would indicate a decreasing time or a slowing down. Which one do we have here? Well, we have the negative sign in the top part indicating the decreased concentration. That does not mean that it's slowing down. We found our average rate of negative 0.03 molarity per second. So it means it's decreasing that concentration per second. All right, on to our next big scientific principle called collision theory. There are 3 important postulates for collision theory. The first postulate for collision theory says that atoms, ions, or molecules must collide in order to react. You can't get a reaction if the two things never touch each other. They have to collide, part of collision theory. There's a little bit more to it. Not only do they have to just bump into each other, they have to have enough energy and be facing the right direction. I think I just said those two backwards. They have to be facing the right direction, meaning they have to kind of fit together like a puzzle, and then they have to have enough energy in order to actually break the existing bonds in order to move on to forming new bonds. So collision theory is going to explain, remember theories explain, how collisions produce effective reactions. What do we need for an effective reaction? We need collisions that have enough energy and are facing the right way, correct orientation. So there's an analogy that I like to use with paper clips. Like picture trying to link paper clips up together. We've all done that at some point, right? In order for the paper clips to end up linked, you have to actually have them touch each other, postulate 1. You have to have them orient the right direction, meaning you have to kind of line up the opening over the metal of the other paper clip. And then you have to have enough energy, or like a force to push to actually link them together for our 3rd postulate. So they have to collide with enough energy in the proper orientation, just like paper clips linking up together. What does orientation really look like at a molecular level, though? Picture something like an enzyme. What it's doing is it's giving kind of a landing spot so that the two things can come together facing the right way. They're much more likely to fit into this lock and key individually, allowing them to combine into the product, rather than the red and the blue thing here just finding each other on their own. If they have a landing spot, it's like they have a meeting place, and so it helps the reaction occur faster. So all reactions do require energy. In the past, we've talked about exothermic and entropy and things that were favorable for reactions happening spontaneously. But all reactions need energy. This is what I'm trying to say. So we've looked at a graph before, kind of, where we looked at the reactants and the product's energy and compared them. And in our first peek at that graph, it was just showing the top and the bottom. It didn't really show an in-between. So I'm going to use a non-graphical version of this first, where this poor little guy is just trying to push this rock up and over the hill. Well, it's going to require a lot of energy to move the rock up the hill. But he's not going to be pushing it down the hill. It will roll down the hill on its own. Chemicals react the same way. So my 2 separate reactants would need energy in order to combine together. Once they're all kind of in position, we call that the activated complex or the transition state, same thing. Then once they're all in place, they don't need any additional energy in order to form the more stable products. So we have this unstable, very temporary activated complex that kind of falls apart into the products naturally. So that bump is called the activation energy. The part of this that we looked at before just showed the level of reactants compared to the level of products. They didn't show the bump. But it's still true that if the energy of the reactants is higher than the products, this would be an exothermic reaction, where enthalpy would be decreasing. Whereas if the energy of the reactants was lower than that of the products, we would still have a bump, and it would be endothermic. So the net change between the product and reactant is always the enthalpy. And then from wherever that leaves off to the top of your bump is your energy of activation energy, which is abbreviated capital E with a subscript of a lowercase a. So this is one of our first important graphs for kinetics. There's a couple of graphs in this unit. This one we have to be able to know where the enthalpy is, where the activation energy is, where the reactants, activated complex, and products are. All right. So I like the little simplicity of the different colors on that graph, but I did want to show you what one would really look like for a reaction where you actually have the different orientations and the actual chemicals kind of progressing. So you've got your activated complex on top, this kind of in between the reactant product positioning. All right, so let's think back. We started talking about things that were favorable for reaction, and eventually that led up to us being able to calculate something called delta G, the spontaneity of the reaction, at the end of our last unit, unit 9. But did that actually tell us anything about how quickly the reaction occurred? Well, no, that's what this whole new unit, that's why it's a separate unit, right? Unit 10 is all about kinetics. So kinetics is the fancy term for looking at reaction rates, reaction mechanisms, how the reactions are going to proceed. So we've got a few factors that will affect reaction rates according to collision theory. The first is the nature of the reactants. Also, you're going to have concentration and, in the same sense, pressure for gases, because more pressure would essentially make the particles more concentrated together. Since gases are compressible, that's the only phase that you're going to have to worry about that for. Then also surface area, breaking up a sugar cube into smaller pieces. Temperature is going to actually have a twofold effect. There are two postulates of collision theory that it actually will use to affect the reaction rates. And then last but not least, we have catalyst, or the opposite of catalyst, by the way, would be called an inhibitor. So let's look at these one by one. I know that was a little fast. So first of all, our nature of reactants. What are the actual reactants? Some substances are more volatile or more reactive than other substances. For example, sodium only has one valence electron. So if you react it with water, you're going to get a very violent reaction. Whereas other substances take a really long time to react. Things like transition metals with multiple oxidation states, they're fairly stable in any way that you put them. So they're not going to be in a big hurry to change. So it's all about like the valence electrons and the different stabilities of the atoms themselves. What are the reactants? Of course, that's a big factor. Next, we're going to look at concentration. So here you have, going from this side, the most dilute solution, all the way up to the most concentrated solution. As we move over towards the concentrated solution, that would represent more and more particles being dissolved in the same volume. Notice how the water level is the same. So if I have more and more particles in there, they're much more likely to bump into each other. They're closer together, and so as they move around, they're going to hit each other. And the more of them in that same space, the more often that will occur. Pressure effectively does the same thing. Let's think about our gas laws. If we apply pressure, we're going to decrease the volume. By the way, pressure and volume being inversely proportional was which gas law? Oh, that was our Boyle's law. So Boyle's law shows that we're going to then get those particles closer together as I increase the pressure. And then because of that, those particles being closer together will collide more often. So again, we're seeing just more collisions overall will increase the reaction rate. Surface area is going to expose more particles to being able to collide into each other. So with a picture like a sugar cube, on the outside, we have particles that can react with this red substance. But if I break up the green stuff so that the particles are now all exposed, I have way more little green atoms that can touch the little red atoms. Whereas up here, the green atoms that can touch are only the ones on the outside. Those are the only ones that can even have access to the red atoms. And as we discussed, you can only have a reaction if they can collide, meaning all of these inside green particles cannot react. When you expose them, you allow them to be able to react. And so that's going to increase the reaction rate. And I mentioned temperature has a twofold effect. Temperature actually hits on two separate postulates of the collision theory. First of all, by definition, temperature is the average kinetic energy of the particles. So if I increase the temperature, I have literally increased the kinetic energy in the substance. That means that there's more energy available for the reactions. And the fact that they're colliding faster means that they would run into each other more often. For example, you're much more likely to have a car accident if you're going way too fast, as opposed to if you're just moseying on your way. So these faster particles are more likely to collide, and the faster particles have more energy. So that's two postulates of collision theory, all supporting that temperature will increase the reaction rate. Last but not least, we have catalyst. So a catalyst is going to speed up the reaction by making a little landing site so that we can have different activated complexes. The orientation can change. It's facilitating that. What that actually means is that we need less energy. So it's a common misconception that catalysts provide energy. All they do is make it easier to occur without as much energy. So that is going to provide the easier way to react. It's going to allow it to combine in a different way, therefore lowering the activation energy. Something else to point out with a catalyst is that it's there for a temporary landing spot. It does not become part of the product. It is not consumed in the reaction. It's the exact same substance at the beginning as it is at the end. You can think of it as like a spectator. All it's there for is to support the reaction, to give it a landing spot that does not require as much energy. And something that would get in the way of the correct orientation would be called an inhibitor, the opposite of a catalyst. The last thing that we're going to look at with with reaction rates is writing a reaction rate law. So this can get a little bit tricky. You want to take it a piece at a time. What the rate law essentially does is compares the rate of the reaction to how the concentration of a reactant affects it. It's only the concentration of the reactants that matter. I don't care about the concentration of the products. So here's an example of rate law. I have A and B being my reactants, and C would be the product. This must be a synthesis reaction. So the rate law would include only A and B. Notice that there's no C. The rate law always starts with rate equals. K is a constant that we're going to have to determine. And then M and N, these exponents, actually kind of describe A's relationship on rate for M, and N is going to describe B's effect on the rate just for each separate reaction, or each separate reactant. If you change the number of reactants, you can change the rate law. Say, for example, I just had A breaking down into B and C instead. Well, then I would only want A in my rate law and not B. I never want the products in the rate law. So you do not get equations for this. You have to be able to format your rate law according to the directions, according to the equations that are given. You have to be able to adjust it as you go. So the general format here is that you always write rate equals, and yes, I will take off the point of that. That's part of the rate law expression. Rate equals K times the reactants, each raised to an exponent. We'll talk about where these exponents come from in just a minute. M is showing you how the first reactant affects the rate. N is showing you how the second reaction affects the rate, and so on. So you can also add together the exponents to get the overall order. M is the order with respect to the first reactant. N is just with respect to the second one. But if you wanted to know the total order of the reaction, you used to add them together. Call it the overall order. So the reaction order itself would be the individual M or N, and the overall reaction order would be what you get when you combine them. Alright, so I'm only really interested in the reactants. Here, this would represent coefficient, and then first reactant, coefficient, second reactant, and then the products. And the reason we're using these coefficients here now on this slide is to show you they have no place in the rate law. We will do a different type of calculation in this unit where the coefficients are part of an expression, but it's not for rate law. With the rate law, it comes from an experiment. We're going to look at some data tables again. Do not let the coefficients become part of the rate law. That's not where they belong. So as we find this rate law, as I mentioned, we're going to look at kind of an experimental data table. The way to determine the rate law is essentially to try the reactant with different concentrations in the beginning. So run the reaction with like a set concentration of A, changing the concentration of B. Then you're going to try it again, having a set concentration for B, and changing the concentration for A. We can look at all these different little trials and compare them so that we can determine our rate law. So the data table would look something like this, where you have A's concentration given in one column, B's concentration given in the second column, and then the experimentally determined rates in the next column. You're always going to have the first column to number them too, so they're easier to keep track of. So let's practice first. What would the format of the rate law be if I have two reactants, A and B? The first thing I would write down is rate equals. Then I have a lowercase k, and I'm going to use my first reactant, which is A, and my second reactant, which is B. So should I write down C also? No, because it's a product. Then I want to use the little letters M and N to represent my exponents, my reaction orders. So the general format is now rate equals K, A to the M, B to the N. And yes, it does matter that it's squared brackets. We're going to plug in the molarities here, the concentrations. So let's give this a shot. I need to use the data table to calculate K, M, and N. I have to find the reaction orders before I can calculate K, so I'm actually going to start with the letter M. M is going to represent how A affects the rate. So I want to make sure A is changing so I can see how it affects the rate, but I also want to make sure B is not a factor. So I want to find where A changes, but not where B is changing. So if I look at A, experiment 1 and 2 doesn't change A, so that would not be a good choice. I can see 1 and 3 do change A, and I can see 1 and 3 have a constant for B. You also see a change between 2 and 3, but notice how B is not constant. So that would be a bad choice. But experiment 1 versus 3 shows a change in A, and it has a constant B. So that means I'm going to use experiments 1 and 3 to calculate M. What I want to do to calculate M is look at the comparison of their rates. Rate ratio as the concentration of A affects it. So I'm basically finding a ratio of the rate to my A, but notice A is to the power of M. So actually M is my unknown when I'm solving for this. That's my X. I need to pick an experiment to put on top, and I would recommend always picking the bigger number. It's just going to make the math a lot easier. If you're good with the calculator, you'll get the right answer either way, but this one's going to make sure that you have, or doing it on the big one on top will make sure you have easy math. So this would be the third rate over the first rate, and the third concentration over the first concentration. So let's start plugging that in. The rate for number 3 was 16 times 10 to the negative 5th over the rate for number 1, 4 times 10 to the negative 5th. So it's rate 3 over rate 1. Now I'm going to put concentration of 3 over concentration of 1. So the concentration for the third one, for A, finding M, is 0.200. And the concentration for 1 was 0.100. Let's not forget that we are trying to find M. So now I'm going to simplify this. 16 divided by 4 is 4. And 2 divided by 1 is 2. But that was to the M power. So what I need to figure out is 2 to what power is 4. The thing about reaction orders is they're always going to be whole numbers. You could have a 0th order reaction, which would indicate that there wasn't an effect by changing the concentration. You could have a first order, which would indicate it's a linear relationship, or you could have second order and sometimes maybe third orders. It doesn't go a whole lot higher than that. So even if you don't know how to solve for the exponent algebraically, you can just plug in, well, 2 to the 0th power would be 1, that's not it. 2 to the first power would be 2, that's not it. 2 to the second power would be 4, bingo. So I know M is 2. So that's one of my 3 steps. Now that we found M, let's move on to find N. So N is going to represent B's effect on the rate. So I'm going to make some room here so that we can look at this table focusing solely on B's effect on rate. I am going to jot down over here because I'll need it later that M was equal to 2. So now let's look at N, which shows how B affects the rate. So if I want to find N, I want to find where there's a change in B, but not A. I want to know that the change in B's concentration is causing the effect on the rate, meaning I need to control A's concentration. So if I look at where B's concentration changes, it does change between 1 and 2, and 2 versus 3. So both of those have a change in B. But where do I have no change in A? That would only be the first two. There is a change here, so that doesn't make sense. So it's going to have to be experiments 1 and 2. Meaning I need to set up that rate ratio. So rate over rate. And instead of concentration of A, since I'm finding N, I'll use concentration of B. So the N. Again, I would recommend putting the larger experiment on the top. So if I'm looking at these concentrations, experiment 2 seems to have the larger number. So I'll put the rate of 2 over 1 and concentration of 2 over 1. So let's plug this in. The rate of the second one is 4 times 10 to the negative fifth. And the rate of the first run through actually had the same rate. The concentration of B in the second one was 0.200, and the bottom one was 0.100. And that is raised to the n power. So let's simplify. A number divided by itself is, of course, 1. And then 2 divided by 1 is 2. And my exponent is on the 2. So the question is 2 to what power gives me 1? The only number that will give you 1 is, see if we make it through this. The only number that gives you, when you raise it to the power of 1 is 0. Anything to the power of 0 is 1. So that means n is 1. I'm going to jot that down to the side. Think about that conceptually for a minute. If the rate is the same when I compare the rates of experiment 1 and experiment 2, even though I change the concentration, doesn't that mean that this concentration doesn't seem to affect the rate? And if you notice that, you don't have to show this work. If the rate does not change as a direct result of the concentration, then that means that the order is 0. 0 would represent that the concentration has no effect on the rate, which we can see here because it didn't change. All right, let's move on to K. In order to find K, oops, I just erased my M and my N. I need to know what M and N are first. And so we just figured out that M is 2 and N is 0. So I'm going to start by basically writing my rate equation so I can bring K into this. But instead of using M and N, I'm actually going to use the numbers now. 2 and then B to the 0. Here's the thing. If the order is 0, that means that that reactant did not affect the rate, then it has no business being in the rate law. So we're just going to get rid of it. So my rate law is actually simplified down to rate is equal to K times the concentration of A squared. In order to find K, you have to plug in some sample data. So I always just pick the first experiment. I want to plug the rate in and the A concentration in and solve for K. So we're going to plug in 4 times 10 to the negative fifth is equal to K. Concentration of A is 0.1. I'm going to square that. So what is K when you take your 4 times 10 to the negative fifth and divide by 0.1 squared? That will give you a K of 0.004. I'm going to add that to my notes over here. Oops, adding 6 things to over here. Actually, I flipped that whole number. 0.004. Now, we have found everything we need in order to write the rate law. But you do still have to finish this up by writing the more generic version of the rate law, something that will apply to the reaction as a whole. So rate equals, remember we have to write that. Now we're going to bring in our K value that's unique to this experiment. Then we're going to bring in A. And now if it told me what reactant A was, I would actually write the chemical formula for that here. Here we're just using a generic A. And then I'm going to write my M, actual number M, 2. Then I have my B to the order of 0. But like we talked about just a second ago, we wouldn't write that because if it's to the 0th power, then it doesn't affect the rate. So this is my final version of the rate law. Plug in K, M, and N. Plug in the chemicals, not concentrations, but the actual formulas. In this case, we're just using a pretend A. Plug that formula into the brackets. Make sure they're squared brackets, and don't forget to write rate equals. Now we have written an expression that shows how the rate is dependent on the concentrations of the reactants. We wrote our rate law. Alright guys, that's going to do it for Unit 10 Notes A. The next set of notes is all about equilibrium. We'll see you there. We're going to be Unit 10 Notes B. We'll see you there.